All right, so this lesson was about machine language, and only part of 1.2 was in that video. The remaining section 1.2 will be in the next video. The homework questions on this will be posted right after this class, and it'll be due next class, 5 minutes before next class. So you need to have a clear understanding of this topic to be able to do those problems. So I'll answer any question you may have. And after that, we'll go over some exercise problems. Okay, any topic here that we should go over?
Can you go over the decimal code, please?
Go over what again?
Decimal code.
Decimal code and, okay. All right, I'm going to begin, hold on. People are still coming in. Okay, the decimal code and binary code. So let me explain what they are, what the difference is. Decimal code means the code we use for numbers. In this code that we use for numbers, if I write 2 digits, like 2 and 5 next to each other, you have learned to read that as 25, and you know that 2 here stands for 2 tenths, 5 here stands for 5 ones. If I write 325, now 3 stands for the hundreds. How many hundreds are there? So basically this number is same as 3 times 100, which is 10 to the 2, plus 2 times 10 to the 1, 10 to the power 1, that's what 2 is, number of tens. And then 5 is 10 to the zeros. How many 10 to the zeros are there? So they're all powers of tens that are counted here. So this is 10 to the 0 count, 10 to the 1 count, 10 to the 2 count. So we put them together and read it as 325, but this is the real value of the number. So basically the actual value of the number, if it is expressed as sum of powers of tens, then these coefficients represent the code of that number. That's how this decimal code works. And you learned to read these numbers and you never paid attention to what they really are, but this is what they are. So the decimal code 325 stands for this expression being the actual value of the number. So in the same way, the next thing is here the 10 is the key number, right? Everything represents power of 10. So 10 is said to be the base of this number system. So we call it decimal. The word deci stands for 10. So decimal system means using 10 as base. 10 as base. Now, why 10 as base? 10 is such an easy number to work with. 10 to the 2 would have 2 zeros. 10 to the 3 would have 3 zeros. We don't even have to do the multiplication. We can just easily work with the 10 to the powers. And that's why we prefer the tens as the base of our system. And, people a long time ago designed the system, and we have been using it without paying attention, but it's because it's so convenient. But after the computers were invented, there became a need for other bases. Using 2 as the basis became necessary, because in computers, we can only represent 2 things. So 2 things, 0 and 1. So therefore, we need a coding system that can use only 1 and 0 as the digits instead of all these 9 digits, 10 digits used in the decimal coding system. Decimal coding system uses 0 through 9, which is 10 digits. We cannot use 10 digits. We cannot represent 10 things in the computer. We can only represent 2 things, 0 and 1. So therefore, we have to use a base that will bring the coding system down to using 2 different things to represent the entire number. And that's what binary coding system is. So we use 2 as the base, then all the coefficients will be either 1 or 0. The coefficients have to be less than the base of the system. So in the decimal system, the base is 10. So all coefficients are less than 10, which are 0 to 9. So if you use 2 as the base, then the coefficients have to be 0 and 1. They have to be less than 2. So if you express the number as sum of powers of 2 and look at the coefficients of that expression, and then they make up the binary code. So binary code is found by expressing the number as sum of powers of 2. And you saw in the video how to find that binary code. And then you also learned a shortcut way to find the binary code. So all those are finding binary codes. That's the difference between decimal code and binary code. So I hope I answered your question, Anthony.
Yes, you did, Professor. Thank you.
You're welcome. Okay, any other question, any other topic we should go over in this lecture 2? All right, then we will practice with some problems. I have some problems already made up to go over today as a way of recalling the information, understanding it better. For the purpose of understanding it better, I have these questions. We'll go over them, and that'll be all we have to do. So this is how it will work always in this course. The videos present you the material. You must go through the video, and you don't have to have the PowerPoint presentation separately opened up. You can if you want, because the video actually presents the PowerPoint presentation with explanation. And whenever the video tells you to do a certain problem, you should pause the video and do that problem, and then continue to play the video. Then I will be actually presenting the solution. So if you do it and then look at the solution, you will learn better. Unfortunately, math and computer science work only that way. You try hard and then you see the solution. It clicks into your brain better. And if you just watch others doing problems, it won't work. You won't learn much from that. So you do it first and then watch the solution. If you watch after watching the entire video, you should start working on the assignment. I will try to post the assignments a little bit ahead of time in the future, so that you can get started with the assignment right after watching the video, instead of waiting for the class to begin. So in the future, I'll post them earlier. Anyway, and also in each class, basically, I'll be taking questions, explaining anything you didn't understand, and then we will be going over some questions like these to get a better understanding. That's how it's going to work. So if anyone who understood everything by watching the video doesn't really have to attend the class, not necessarily, but as you can see, practicing with these problems would be always helpful. Right now, the course is at the very beginning, and this is very easy, but things will get harder as we proceed. Like I said before, this course is challenging, okay, not very easy. So you have to follow the method, follow the course the way it is designed very carefully. If you get lost, it's very difficult to very difficult to catch up. So don't get lost. Try to be with the class by watching the videos at the right time and asking the right questions and so on. So the second assignment will be due I hope everybody has turned in the first assignment, and I will be grading them today. And so sometime tomorrow, you should be able to look at your solution. I explained how to look at your assignment after grading. 1 second. You have to go to the grade book and go to that assignment, and the assignment name itself is a link to your assignment, and you can view the graded assignment. You should view the graded assignment to see my explanations as to why you lost points, because those explanations would be a way to learn what went wrong and how to do it right and things like that. So sometimes tomorrow you should be able to look at, or even later today, you may be able to see my comments and grades for your assignment. And the next assignment will be posted right after this class, and you need to do that before next class. Okay, so let's begin with this exercise, class 2 exercises. First one says, find the binary code of one.
Excuse me, Professor.
Yeah.
Someone has a question. They said in chat.
Oh, in chat, okay. Why is that person not asking the question? Having some.
Professor, it's Neil, your student.
Yeah.
Can you hear me?
Yes.
I sent you an email early this morning because I'm right now at campus and they're not letting me in, so I had to join virtually on my phone because my phone's Wi-Fi connection is pretty bad. So I had to join that way. So I don't know if I'll be able to be on campus because the reason why I came on campus, after your class, which is virtual, I have a on-class campus that I'm not gonna be able to attend today. So that's why I emailed you, and I hope you got the email. So sorry about that.
Okay, that's all right. I mean, attendance is not required for that same reason. You may on Mondays particularly, you may have other classes scheduled or other things to do. So yes, I understand.
Will I be penalized or no?
No, you won't be penalized.
Okay, thank you. No problem.
It's,
I just want to let you know. So yeah.
but
it means it's not mandatory to take this class?
no, the attendance is not mandatory. But as you can see, attending and asking your questions is helpful, right? And also I'm going to go over all these questions and problems, and so you will get better understanding after that. So the classes are designed to help you better, but not required.
All right, thank you, Professor.
Yeah, particularly Monday is not required because the Wednesday is
Thank you, Professor.
Yeah.
If I do pick out, I may need to rejoin. So just letting you know of that.
Yeah, I recommend attending the class for the reason that it helps you understand things better. All right. And also the rewards are given only for those students who attend all the classes. You have read about the rewards. So, there are benefits in attending the class, all the classes, but attendance will not, missing classes will not affect your grade directly. Okay, so you're not penalized for missing classes.
Professor, if you attend every single Wednesday class, you don't get penalized for rewards, correct?
Actually, no, the rewards for students attending all the classes.
So Monday and Wednesday.
Yeah.
All right.
Unfortunately, that's the purpose of the reward. I mean, the reward is helpful with the grade. I mean, at the end of the semester, it will help your grade boost it up a little bit. But nobody is going to be penalized in any way for not attending the Monday classes. Okay, that's the way it's designed, and we have to stick with that. So if for the rewards, if you are asked after the rewards, then you have to attend Mondays and Wednesdays. Any
I have
further?
a question, Professor, about one more thing from the video.
Yeah.
Is can you explain a little bit further of octal code? I just was a little bit confused about that.
That's not in this video. That's in the next video, I believe.
Oh, sorry. I just went ahead a little bit in the textbook. My bad.
Yeah, you should bring up that after watching the video that explains that topic. Okay. Now, in this video, only part of 1.2 was discussed, all the way to binary codes and memory bytes and things like that. I believe the octal code is in the next video. Am I right? Anybody? Is it in this video? I don't believe that. Okay, so wait for the next class to bring up questions on octal code and hexadecimal codes. Okay, Chris, did you ask the question? Chris Barron?
Yes, yes, I did.
Okay, so I believe it's in the next video. So you must have read the book instead of watching the video. So watch the, please bring up the question on octocode and hexadecimal codes only after watching lecture video 3. Okay, one student is asking me about attendance. Am I taking attendance? Yes, I always take attendance about 1 minute into the class. And I take attendance not by calling names, but yeah, this student is wondering how I took attendance. Here's how I take attendance. When after everybody has joined the meeting, Zoom shows me the list of names of students who have joined. And I just take a screenshot of that list, and that shows me who is in the class. And when after that, if someone comes late, I had to write down the name of that person and mark that person as late attendee. That's how I take attendance. So you will only hear me taking a screenshot, a sound coming from the screen when I take the screenshot. That's when I'm taking attendance. All right. So I took attendance at the beginning, and after that, some student came in and I wrote down the names. So I have the full attendance record. Okay, so moving on. Feel free to bring up any question in the middle of the class anytime. You know, this whole class is for discussing and understanding everything better. Okay, so we're doing the first question. Find the binary code of 115. You can use the shortcut method or the long method and find the binary code. Go ahead and do that on the paper and tell me the answer. Okay, anybody has an answer? You can go ahead and tell me what the answer is. Anyone with the answer, go ahead and tell me the answer. I'm assuming all of you are working on this problem.
Professor,
Yes.
is it 1110011?
Right. Very good. 1110011 is correct answer. Excellent. I hope everybody tried that problem. Anybody wants explanation? Okay.
Professor, I have a question.
Yeah, go ahead.
When you're trying to find the binary code, right?
Uh-huh.
The ones and zeros that represent the circuits, correct? When you're moving down the equation, so like I started off with like 1 times 2 to the 6th power,
Uh-huh.
and moving on to 1 times 2 to the 5th power, and so on, so on. For the numbers that add up together, um a 1 will be in front of it, correct, to represent that it's on, and then a 0 will
When
be.
you are actually storing this number in the memory, every 1 will be represented by a circuit on, every 0 will be represented by a circuit off. Yes, when you store it in the memory. Right now, our question is, what is the binary code? You don't have to worry about storing it in the memory when you're finding binary code.
All right, thank you.
Yeah, so the answer to the question here is 1110011. Now, how did we find it? If anybody has a question on that, I can go over. I think there was one student, Olga, you raised your hand. What, is that a question or?
I just wanted you to explain it, please.
Explain how I got this?
Yes.
Okay. All right. There are 2 ways. One, the first method is a little bit longer and it'll take longer work. And you watched it in the video. And then I explained the second one, which is a shortcut for finding the binary code. So I'm going to use the shortcut. The shortcut is always easier way. So there's no reason to use the other method. The other method is for understanding it, understanding the binary code better. So I'm going to first show you how to find this binary code by using the shortcut method. What you do is you start with the 115 and divide it by 2 and write the answer here and write the remainder on the side. So 2 goes into 11 5 times and 1 remainder. So I have 15. 2 goes into 15 7 times with the remainder of 1. So that remainder we write on the side like that. Okay, so keep doing it repeatedly. Keep dividing by 2. 2 goes into 5 twice. I have 17, 8, 1. So keep doing it. 14. 2 goes into 28, 14 times with no remainder. When there's no remainder, you write 0 as remainder. Okay, 2, 7, 0, 2, 1. At the last step, 2 goes into 3 1 time with the remainder of 1. You still have to write the remainder. So now we have finished. When the number is less than 2, that's when we stop. Number has become 1, so we stop. Now, if you read these digits, starting with this 1, read these remainders backwards, bottom up. That'll be your code. So this last one here is the one I'm writing. This is the one I'm writing next to it. This is the next one. 1. And then 0, 0, 1, 1. That's our code. So all these remainders, including this one, last one, reading from bottom up. That's your code. Okay, so realistically, what this means is the number 115 is equal to, see, this last one represents 2 to the 0. This represents 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6. So this first one represents 2 to the 6 plus 1 times 2 to the 5. This one represents 2 to the 5. Next one represents 2 to the 4 and plus, that's plus. So 2 to the 6, 5, 4, these are zeros. So they don't contribute anything, but this is what it means. 0 times 2 to the power 3 plus 0 times 2 to the power 2 plus 1 times 2 to the power 1 plus 1 times 2 to the power 0. This expression is equal to 115. If you actually simplify this whole expression, it'll be equal to 115. So when the 115 is expressed as sum of powers of 2, the coefficients of those powers will represent the code. That's what the binary code is. So 115 is the binary code. I mean, this is the binary code of 115 means this expression evaluates to be equal to 115. That's what it means. So that's the meaning of binary code. Okay.
Thank you,
so
Professor.
you're welcome. And anybody else needs explanation on that? Any other question on that? Okay.
So Professor, so Professor, to check the binary code, the 1110011, you could put into basis of 2, right? Because that's what I was about to ask you, and you got into it immediately.
Yes, to check, to verify this is the code, you can add up, you can write up this expression and add up. These will add up to 115. Okay. So in fact, that's how you go back from binary code to decimal code. See, this is the decimal code of the number whose binary code is this, right? These are both the same numbers in 2 different coding systems. So if I ask you, if I give you this and ask you to find decimal code of this binary number, then you have to write this expression and simplify. That'll give you the decimal number. So yes, this they both represent the same number in 2 different coding systems.
So that's the binary expression for that number, right?
Right. Exactly.
Thank you.
So the second question, number 2 says, find the decimal code of the binary number. So I just explained a minute ago how to do that. See, if I give you this binary number and ask you to find the decimal equivalent, then you had to write this expression and simplify it. That'll give you the 115. So 115 is the decimal code. That's how you do it, number 2. So go ahead, do number 2 and tell me the answer. I'm assuming all of you are working with this problem. I don't see you. I'm not seeing anybody. Well, by the way, it's okay to have the video off, but at least, you know, if some of you have the video on, I'll feel like I'm teaching some humans. Otherwise, I don't, you know, I'm not seeing any human here. So it'll be nice if some of you can have the video on. All right. Anyway, I'm assuming all of you are working on the problems I give you, because that's what this class is for. You need to work on the problems to learn better. So problem number 2, I want you to do and tell me the answer. If anybody has the answer, please go ahead and tell me.
Well,
Yes.
the answer for number 2 will be 155.
Okay, one student has 155 as the answer. Anybody else?
I also got 155.
You also have 155. Okay. Okay, very good. That is correct answer. And I'm glad to see at least 2 students got that right. I don't know what the others have. Anyway, 155 is the answer. Number 2, answer 155. Anybody wants me to explain?
Can you explain how it's
Yeah.
155?
All right. Okay, I'm going to go over that. The number given to us is 10 10 11 0 1 1. Okay. So to find the decimal equivalent, I have to write the expression. This expression I explained before. This last one represents 1 times 2 to the 0. So when you start at the last one, it'll be easier. The next one is 1 times 2 to the 1, this one. And the next 2 are 0. The next one is 0, so it's not going to contribute anything, but I'll write it down just to show you. I think you should mute. Kevin, can you mute? I'm muting you. So 0 times 2 to the 2, and then this one represents 2 to the 3. So 1 times 2 to the 3 plus 1 times 2 to the 4, this one right there. Let me move the screen over a little bit, okay. And after that, I have 0 times 2 to the power 5 plus, hold on, let's count. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, okay. 1 times 2 to the 6, okay. So you do that, and then you have to simplify. Did I copy it wrong? Yeah, I missed it 0. That's what I thought. 1 0 0. So there's a 0 here, and then 1. Sorry about that. So that's 0 times 2 to the 6 plus 1 times 2 to the 7. Okay, so that's the expression. Now I have to simplify. So here I have 1 times 2 to the 0, that's a 1. And 1 times 2 to the 1 is a 2. That's a 0. And then I have 1 times 2 to the 3, that's 8. Plus, this is 16. Plus, this is 0. And then 0 times 2 to the 6. And then this 2 to the 7 is 128. So the others are zeros. So now add up the 128, 16, 8, 2, 1. That gives you the 155. Okay, so 155 is the decimal code of this binary number. Okay. Any other question on that problem? All right, going over to number 3. It says ASCII code of a character is, so the ASCII codes of the character, every character in the English language has an ASCII code, which consists of zeros and ones. exactly 8 zeros and ones are put together for each character. Character means not just alphabets, other things too, even a question mark or exclamation point, period. All these symbols have ASCII codes. And so these ASCII codes, if you treat them as binary codes of number and convert these ASCII codes to decimal code, you will get a number. So in other words, in the video, I used an example of the character A. The character A has a certain ASCII code. I think, yeah, I can look it up. Right here, I have it. 0, 1, 0, 0, 0, 0, 5 zeros, and then 1. Okay, this is the ASCII code of character A. And if I convert this, this is also, you know, as you can see, it looks like a binary code. So treating this as a binary code of a number, if I convert it to decimal, the decimal number is 65. So in other words, storing the character A in the memory would be same as storing this code, which is same as storing 65. So in the memory, storing A and storing number 65 are same. So how does the computer know whether you have stored A or 65? It doesn't, and it doesn't have to know. The programmer can extract that data as a character A or as a number 65, whichever way he or she wants. So when you store the character A or 65, you have exact same thing stored in the memory. Similarly, all other alphabets have corresponding codes, all the way to capital Z. Capital Z corresponds to 90. So the 65 to 90, this range represents uppercase A through Z. So these are called decimal codes of the alphabets A through Z. Lowercase a corresponds to the number 97. The ASCII code of A corresponds to ASCII code of 97, binary code of 97. And lowercase z corresponds to 122. So these digits 97 to 122, all of those are considered to be the decimal codes of characters A through Z. So it's when you're writing computer program, if you need to recognize whether the character we have is a lowercase alphabet or not, this is what you do. You compare that against 97 in this range to see if it is. You compare the value decimal equivalent to 97 and 122 to see if it is in that range. If it is in this range, then it is lowercase alphabet. If the decimal equivalent of the character you have is in this range, then it is uppercase alphabet. If it is not in this range and not in this range, then it must be some other character. You know, all other characters are coded too. So that's how you figure out. I mean, in computer programs, we have to sometimes figure out what kind of letter we're dealing with. So this is how you figure that out. So in order to give you the understanding of that, I have this question. ASCII code of the character, certain character is this, 0, 1, 1, 1 all the way. There are 8 bits there. What is the decimal code of that character? Which will be the decimal equivalent of this binary code. So I'll go ahead and find the answer and then answer the second question. First, you have to find the decimal equivalent of that ASCII code. If anybody has the answer to the first question, go ahead and let me know.
I got 127.
All right, one student has 127 as answer for 3.
I got 127 as well.
Okay, 2 students have 127. Anybody else?
I also got 127.
All right, very good. 3 students have 127, and that is correct answer. So the answer to question A is 127. Now, anybody needs explanation on that? It's the same method that I explained for the previous problem. I showed you how to find the decimal equivalent of this binary number by writing this expression and then simplifying. It's the same method. If you use the same method, you will get 127. All right, so I guess everybody understand that. So let's answer the part B. It says, is this character an alphabet? So we are talking about a character whose ASCII code is given, and we found the decimal equivalent. Now the question is this character an alphabet? Anybody has an answer?
Is it no? Because it doesn't seem like it's within the range of 65 and 90 and 97 and 122, correct?
Exactly, very good. That is correct answer. The number 127 is not in the range 65 to 90 or 97 to 122. So therefore it is not alphabet. So the answer is no. Very good. Okay, going over to problem number 4. Problem 4 says, if the binary number given in problem 2 is stored in the memory, show the memory setting. So it wants you to show the memory setting when you store that binary code given in problem number 2 is stored in the memory. So all you have to do is show the, remember when you store it in the memory will be set on and off according to the binary code. Every 1 will be represented by an on, every 0 will be represented by off. So we need a circuit turned on for the first one. So it's 1 0 0 1 1 0 1 1. So you can show the answer this way. First circuit will be on, another circuit will be turned off, another circuit will be turned off, and then on. On is a complete circuit, off is a broken circuit. That's all it is. So this is one way. But when I give you the test, the test will be on Blackboard, and you won't be able to draw these circuits there. So I'll ask you to just write the words. So off, on, words. So you'll be writing on, and then off, off, on, off, on. And that's it. Write it with space. Write these words with single space in between, and that'll be a circuit setting. That's the answer to number 4. But when you're doing the assignment, you can show the circuits this way. But if you write it this way, I can't reject it, but I prefer you to show it this way if you can. Going to number 5. What is a bit? Can anybody answer that?
8 bytes.
A bit.
No. No, you have it reversed.
Oh, 8 bytes is, oh, never mind. Sorry.
Okay. The question is, what is a bit? Anybody can answer.
Yeah, I'll try.
Okay.
I put a bit stores binary code, so zeros and ones, which are used to store information, such as a character like an A or the number 3.
Yeah, No, not so much. You already had said the answer.
Okay, so it just stores binary code like zeros
It,
and ones.
it's the 1 or 0 found in the binary code.
And found in binary code?
Yeah, when you write
Okay.
binary code or ASCII code, you have ones
Yeah.
and zeros here. Those ones and zeros are called the bits. Okay, these are the bits.
Okay.
So when you have a ASCII code of a character, there will be 8 bits in it. Means 8 zeros and ones will be in it. Okay. So to answer the question number 5, the way you would answer it is the 1 and 0 used in the binary code or ASCII code is called a bit. All right, that's the answer.
So it's short for binary digit?
Yeah, if you say binary digit, that would be correct, but we call them bits instead. That's a standard word in computer science. Okay, so 1 byte of memory consists of how many bits? Okay, yeah, I mean, you have watched the video, so tell me the answer to that.
Contains 8.
8. Because the ASCII code of all the characters have exactly 8 bits in them, the one byte, what we call 1 byte of memory, is 8 bit of memory. In other words, 8 circuits. Basically, physically, there are circuits inside the memory for you to store data in it. So if you take exactly 8 of those, that's what we call 1 byte. This amount of memory is called 1 byte. So 1 byte of memory has exactly 8 circuits. So what you really find in the memory is 8 tiny circuits put together is called 1 byte of memory. And by turning these circuits on and off, you're storing the character in it. So if you're storing this binary code in 1 byte of memory, then the 1 byte of memory will be set to these. It'll be set to these on and off. So those circuits are going to be turned on and off according to the binary code or ASCII code. So the storage space needed to store 1 character is what 1 byte is, which is same as 8 bits long. Okay, so there are several things I said. 1 byte of memory consists of how many bits? 8 bits. And so when you store a character, how many characters can you store in 1 byte? 1 character, because 1 character needs all 8 bits. If the question says, what is a byte? Then you can say a byte has 8 circuits or 8 bits, or it is the memory needed for storing 1 character. All those are correct answers. Okay, so the answer to question number 6 is 8 bits. Question 7 says 1 kilobyte consists of how many bytes?
1,000.
1,000. So we use 1,000 as the steps for all the measurements of memory. So 1 megabyte consists of 1,000 kilobytes. So 1 kilobyte is 1,000 byte, and then megabyte is 1,000 kilobyte. So the next question says 1 megabyte consists of how many bytes? Anybody?
Is it a million?
Million. 1,000 times 1,000, which is 1 million. So 1 million bytes are there in 1 megabyte. Next question says, how many bytes are used up when you store the character W in the memory? What's the answer?
Isn't it just 1 byte?
1 byte is correct.
Okay.
One character needs 1 byte of storage. That's correct. Number 10 says, how many bytes are used up when you store the word exorcist? I misspelled it. Okay, how many?
8 bytes.
8 bytes is correct. There are 8 characters. Every character needs 1 byte. So this entire word will take up 8 bytes of storage. Okay, next question says, if there is 1.32 megabyte of space left in a storage device, see, not only memory, any storage device, such as disk or hard disk, they all use the same idea to store characters. Every character is coded in Ascii code, with ones and zeros. And when you store the character in any media, the ones and zeros are getting stored. So the memory and storage media, they are all measured with these bytes and kilobytes and megabytes. So if there's a storage device, such as hard disk, that has 1.32 megabyte of space left, how many characters of data can be stored in it? Now, remember, when they ask you how many characters, you had to provide a whole number answer. Okay, like 2,000, 5,000, whatever the whole number is. Do not give a fractional answer. So how many characters can be stored in this memory? Anybody has an answer? All right, let me explain. If you have 1.32 megabyte, then you had to convert it to bytes, because every byte is good for storing 1 character. Well, we know that 1 megabyte is 1 million bytes. So 1.32 megabyte is 1.32 times 1 million bytes. You can use calculator if you want, but this is the same as 1,320,000. 1,320,000. That's what that is. And so your answer is, that's how many bytes are there. And we know that every byte is good for 1 character. So that's how many characters. All right. So you provide the answer this way. But if you say 1.32 billion, which is correct, but that's not how you answer when they say how many characters. You really have to convert it to a whole number.
Professor, can you briefly explain that once more, please? Because I'm still a little bit confused.
Which one? This question, 1.32 megabyte?
Yeah, please.
Okay. We know 1 megabyte is 1 million bytes, right?
Yep.
Yeah. So 1.32 megabyte is 1.32 times 1 million bytes.
Okay, copy. It's just as simple as that, correct?
As simple as that.
All right. Thank you. I was just making sure.
Because this is how many megabyte we have, and every megabyte is 1 million bytes. So if you just multiply by 1 million, that'll give you the number of bytes there are. And that number comes up this. And so there are 1,320,000 bytes in there, which means that many characters can be stored. Every byte is good for 1 character.
Quick question, Professor.
Thank you.
Professor?
Yes, go ahead.
So let's say if it said 1.32 kilobytes, then it will be 122 times 1,000, which is 1,320. Or
yes, 2 times 1,000. Because if it says 1.32 kilobytes, then every kilobyte is equal to 1,000 bytes. So you need to multiply by 1,000, and that'll give you 1,320.
Okay, thank you.
And you have background noise, so keep yourself muted as much as possible. All right, going over to the next question, which is how many characters can be stored in 1 megabyte of memory? Anybody?
$1 million characters?
1 million characters. That's it. 1 megabyte has 1 million bytes. What is the largest number in decimal code that fits in 1 byte of memory? This was discussed in the video. Anybody remembers the answer can tell me. The largest number that fits in 1 byte of memory. All right, let me explain that. 1 byte of memory has 8 bits, right? If I want to store a number in that 8 bits of memory, then that number can have 8 bits, 8 ones and zeros. Now, in the 8 bits, if there is any 1 0, then that number is not the largest. If I replace that 0 with a 1, the number will be larger. Agree with that? Right? If I replace this 0 with a 1, the number will get larger, right? So therefore, the largest number that fits in 1 byte should have 8 ones in the ASCII, in the binary code. Do you all agree?
I agree.
Okay.
Yeah.
If any one is a 0, that's a smaller number. We are looking for the largest number that fits in 1 byte. So that number will have 8 ones in its binary code. So we have to have the decimal code for the answer. So I have to convert this to binary number, 2 to the 0, 2 to the 1, plus 2 to the 2, all the way to 2 to the 7. This last digit will represent 2 to the 7. Okay, you can individually simplify these and add them up. That'll give you 255. So that's the answer. 255 is the largest number that fits in 1 byte. But let me take this moment to explain something you learned in the video, but I wanted to explain that better. This is a series called, it's a geometric series with the common factor being 2. I don't know, some of you may have learned geometric series, some of you may not have, but for series, there are formulas to answer. So this series can be, this series is same as 2 to the 0, let me write, 2 to the 0 is a 1, so 1 plus 2 squared plus 2 cubed, all the way to 2 to the n. If it stops at n, the sum of all that is equal to 2 to the power n plus 1, 1 larger than the last power, minus 1. This is the value. It's a formula. Any series like this will be equal to this. So if I want to find this series by using this formula, it's equal to what? 2 to the power what?
8.
8. 1 more than the highest power, minus 1. 2 to the 8 you can find in your calculator. By the way, you need a calculator, scientific calculator that can find exponents when you take your test and when you do your homework too. So if you don't have one, you may want to get one. 2 to the 8 is 256. After subtracting 1, you get 255. That's your answer. So you need to learn to apply this formula because this kind of question will be asked later for a larger amount of memory. So you have to use this formula. Direct math will be difficult. You know, adding up, calculating 2 to the 7 and then 2 to the 6 all the way down to 2 to the 0 and adding them up is a long work. If you apply this formula, you get to the answer faster. So this formula you need to memorize. It came up in the video and it's in your book. It's everywhere. You need to remember that. You need to memorize that formula. All right, so next question is, how many bytes are needed to store the number 1375 in the memory? Okay, there are 2 ways to answer that question. one way is to find the binary code. And remember, 1 byte is 8 bits. So if a number has more than 8 bits, then it needs more than 1 byte to store. So that's the way you can answer it for now. So we should, if you find the binary code of 1375, you can answer the question. What is the other way? Anybody can see another way is there to answer this? All right, before that, let me ask a different question. We have some time. What is the largest number that fits in 2 bytes? If your number is bigger than 1 byte, then you need 2 bytes. So let's say I have 2 bytes available. Largest number I can store here is what I need. Okay, that will be all ones, right? The number that has 16 ones. There are 8 bits here and 8 bits here. If 2 bytes are together, then there are 16 bits altogether. So the largest number that fits in 2 bytes will have 16 ones in it. So how do I convert that to binary decimal equivalent? It'll be 2 to the 0, 2 to the 1, 2 to the 2, all the way to what power will be the largest? 2 to the power what?
$16.
Not 16.
Is it 15?
What's that?
I said 15.
15 is right, yes. Because we are starting at 2 to the 0, the largest will be 2 to the 15. The 16th bit will have 2 to the 15. Just like here, 2 to the 0 to 2 to the 7 when you have 1 byte. So when you have 2 bytes, it's 2 to the 0 to 2 to the 15. Okay, now to sum up this series, what would that be? What's the sum of that series applying that formula that you learned?
Is that 510? Professor, is it 510 or no?
No, you're doubling 255. No, it doesn't work that way.
Oh, okay.
2 to the 16th minus 1.
2 to the 16 minus 1. That's right. Okay, so you have to use the calculator to simplify that. You have to use calculator to simplify that, and it'll come up 65,536. After you subtract the 1, it'll be 65,535. This is the largest number that fits in 2 bytes of memory. Okay, so 255 is the largest number that fits in 1 byte of memory. 65,535 is the one that fits in 2 bytes of memory. Now you should be able to answer the question number 14 without doing any work. How many bytes are needed?
2 bytes.
2 bytes.
2 bytes, exactly. Very good. Because it's bigger than 255 and smaller than 65,535. So anything smaller than 65,535 can go in 2 bytes. And therefore, this will need 2 bytes. So that's the second way to answer the question. But to answer the question in the second way, you had to remember these numbers, 255 and 65,535. You're not required to remember those numbers, but if you remember them, you can use the second method. Otherwise, you had to find the binary code and figure out how many bytes are needed. If it has more than 8 bits, then it was explained in the video that if you have more than 8 bits, then the last 8 bits will go in a second byte and the first 8 bits will go in a first byte. 2 bytes have to be together. So when you have 2 bytes together, this byte represents 2 to the 0 and this this bit represents 2 to the 7. Now this bit represents 2 to the 8. And that's why it's not twice, it's not double of 255, because these bits represent larger numbers, 2 to the 8, 2 to the 9, all the way to 2 to the 15. So much larger than 2 times 255 can fit in here, which is 65,535 to be accurate. Okay, so even if you don't remember these numbers, 255 and 65,535, you can quickly calculate that, right? If it is 1 byte, then there are 8 ones. 8 ones means this is the largest number that fits the binary number, and convert it to, use this formula, come up with this number. Similarly, for 2 bytes, do the same thing, you'll come up with this number. You can quickly calculate, but you have to be able to calculate them. There will be questions that ask you to determine the largest number that fits in 2 bytes, 3 bytes, 4 bytes, 5 bytes. Any of those can be a question in the test, question in the homework. So you have to be able to figure this number. All right, if there is no other question, I'm done with today's work. Anything else?
The next homework assignment is due before the Wednesday class, correct?
Right. Next homework assignment will be due 5 minutes before the next class. And this time I'm going to post next assignment and the following assignment early so that you can get started even before the next meeting on the third assignment. I'm giving you the option.
Thank you, Professor.
You're welcome. That's all I needed to discuss, and I hope this discussion helped. That was the purpose of it, and we'll continue to do it this way. And always attending the class is beneficial to you. You will understand a little bit more. And so I strongly advise you to attend all the classes. The students who attends all the classes and does all the work will definitely be successful with flying colors. Okay, enjoy the rest of the day. We'll see you Wednesday.
See you Wednesday, Professor. If I have any questions, can I email you for office hours?
Yes, you can email me or you can meet with me during office hours. Office hours will be 3 to 4 this evening.
Thank you very much. Have a nice day. See you
Professor,
Wednesday.
I just had one question. What was the 255 for?
255 is the largest number that fits in 1 byte of memory. Okay. So I went through this calculation to show you why 255 is the largest number that fits in 1 byte.
Yeah, correct. Thank you so much. I appreciate it. Have a good day.
Professor, are we meeting in person on Wednesday or is it online as well?
No, it'll continue to be this way.
Okay.
Online.
Okay.
Yeah.
All right. It's just because on CUNY First it says in person.
I know it says that, but our faculty senate is in disagreement with that, and they
Okay.
that's not true. Okay.
Right.
I have a question. When you meet faculty senate, do you mean like the senate for like all of the classes or just for like computer science?
No, senate for all the faculty members.
Oh, I see. So like the ones that are still like in person, are they working to making those online as well, or?
Yeah, there are some classes still online even after they wanted us to meet in person, and some classes are meeting in person, so it's a mix.
I see. All right. Thank you. Have a good day.
You too. Bye-bye.
All right. Thank you, Professor. Goodbye.
Yeah, goodbye.
Have a good day, Professor.
Have a nice one, everybody.
Thank you, Professor. Have a nice day. Thank you.
Do we have any due today for the next week?
Yes, there will be assignment due next Wednesday.
All right.
Yeah, before every class, there's an assignment.
All right. No problem.
Yeah.
Thank you, sir.
Yeah, thank you.